Hello, everybody. It's Professor Fiore, and it's time for more network fun. If you haven't seen the first network fun video, strongly suggest you take a look at it. We're going to extend the idea with some further resistor craziness. So the thing I want to focus on today is the fact that usually in the electrical engineering field, we tend to think of circuits as these sort of flat, planar kinds of things we can draw on paper. We think in terms of 2 dimensions. Right? We typically don't think in terms of 3 dimensions. As a matter of fact, the tools that we use, a simulator like Tina TI here, is designed specifically to do that. And further, we are constrained in terms of orienting our components in a horizontal or vertical form. It is the very rare simulator that would allow you to rotate a component at an arbitrary angle. Right? It's just typically not done. We're very used to this whole up, down, left, right kind of thing. So we don't think in terms of 3 dimensions. Unlike maybe someone who's, an architect, right? They pretty much always think in terms of 3 dimensions. People are going to move around in a building up and down as well as left, right, back and forth. So that doesn't mean, just because we don't tend to think in those terms, that doesn't mean that there's got to be, some new kind of electricity set of rules or something like that. All of our rules still work. Our circuits don't really care about gravity for the most part. So you don't worry about taking, an electronic circuit and holding it upside down and the electrons are going to leak out the bottom, right? That doesn't happen. So it's kind of interesting to sort of refocus, right? So here's a good one. A cube. So imagine each one of these lines is a resistor. Okay, so maybe I have a current source back here. I'm going to fire that into one of these nodes. I'm going to ground the other end, and I want to see what happens. And of course, in keeping with our network fun, I'm going to make this consistent and have all of the resistors in here be the same size. And the question is, hey, can you apply the rules, Kirchhoff's voltage law, Kirchhoff's current law, Ohm's law, etc., and determine what the voltage, let's say, at this node is, right? Or what the current through these various resistors happen to be. All right, you ready? So the first thing I want to point out is trying to draw a resistor cube in a simulator. I've used several simulators over the years, and like I said, generally speaking, they pretty much enforce this idea of a horizontal or a vertical orientation. Sometimes you can draw wires at angles, but even that is not always an easy trick to do, right? Components, forget about it. But again, it's typically not something that you need to do, so I'm not in any way complaining to the software manufacturers, right? I mean, it's perfectly logical what they're doing. But trying to draw this in the simulator is a little bit cranky, all right? So here's an attempt. Oh, it doesn't look much like a cube, does it? All right, so here's what I had to do. Here's like one side, like one face of the cube, right? So 4 resistors, all 1K. Here's another face. And then what I have to do, so you can think of this, right? You think of these two as like this backward square here and this front square, or, depending on how you look at this, this might be the front and this might be the back. But, fun optical illusions. But anyway, the obvious squares that look like squares, right? Those two things is what I'm drawing as squares. And then these angled ones that would be coming out or going in, those I have to kind of play with here in terms of the orientation. So that's what these resistors are, right? This one, this one, this one, and this one. So like I said, here's one of the squares, here's the other square. And then what I have to do is connect a resistor from this upper left corner to this upper left corner. So that's what this guy is, which normally would be at an angle. And then the same thing over here. For this upper right, I need a resistor to go to this upper right. So that's what R9 is. Again, ideally it would be at an angle. And then the same thing happens down here, right? For the lower left, there's R12. And then for the lower right, there's R10. I mean, I had to kind of throw that one out here because otherwise it would get really messy. So in any case, I've got all these 1Ks, and I want to figure out what the voltage is at this node, at VA. I'm going to pump a 12 milliamp current source into this thing, right? Now, before I go any further, note that there's really no simplifications that you can do. You can't go back and say, you know, Rx is in parallel with Ry, or Ra is in series with Rb. Let me add these together. Let me do some kind of combination. It's not going to work. All right. So if we look at the little simplified 3D model here, go ahead. Try to find two resistors that are in parallel or that are in series. You're not going to. So what do? Where do we go? Well, you still have KVL. You still have KCL. You know, it's Kirchhoff's current law. It's not Kirchhoff's current pretty good suggestion that works most of the time. It still has to be true. All right, so you might want to pause the video at this point and, you know, whip out a piece of paper and start sketching around and seeing, you know, what can I find here, right? You know, what's going to happen with my current? What's going to happen with the voltage? You know, you could try to find the total resistance, and then knowing the total resistance, you know the current, so you could just use Ohm's law to find VA. Or you could just try to apply things like KVL and KCL to come up with, you know, ultimately VA, perhaps by finding, you know, drops across various resistors. Okay, you know, there's lots and lots of paths here. You know, if the point is to find VA, right, from this node to ground, remember, you can take any path from one point to another, no matter what that path is. You got to get the same voltage. So for example, you could say, well, it would be the drop across to R11, right, plus the drop across to R5, plus the drop across to R8. That's one way to do it. You could say it's the drop across to R1, plus the drop across to R9, plus the drop across to R8. And there's a whole bunch of ways you can do this, right? R3, R2, R10, okay? It just goes on and on and on, right? R1, R7, R6. So those are things you can try. So again, you might want to pause the video at this point. I'll wait patiently. All right, enough of that. Let's take a look what we can do. I'm going to do a little color coding on here. I want you to consider this. Remember, all of the resistors are the same. So when I get to this red node here, these three currents have to be the same current. Right? Excuse me, they have to be the same magnitude, not the same current. Right? They have to be the same value. Why is that? Well, since we're going from one node to the exact opposite node, no matter which way you take, right, this top one that's going straight up and down, this diagonal one, you're going to have to go through the same number of resistors, the same values, to get back to ground. In other words, no matter which one it is, right, you could just imagine rotating this cube around. There really is no functional difference between taking one path or the other. So for example, right, if you took the upper path, you have to come through here, you get to this node, the current splits, and I'll just take the upper path. We get to here, and again, I'm going to take the shortest path to ground. That's the blue back down. If I took this path for black, I'd get to here, and it's blue back down. So it's red, black, blue. If I were to take this path, it's red, again, splits, either way, black, and then again, either way, it's blue back to ground. If I take the diagonal, red, split to black, and then again, blue back to ground. It doesn't matter. And that's primarily, like I said, because it's symmetrical, right? All the resistors are the same. If they were different sizes, well, you couldn't say that. The paths would be true, but the currents could be different. So if that's the case, and we started with a 12 milliamp current source, if that's the case, then the three red paths should divide that equally, right? KCL, sum of currents entering, 12, has to equal sum of currents exiting. So this is going to divide evenly. So I'm going to have 4 milliamps, 4 milliamps, and 4 milliamps. Now with 1K resistors, that would be a 4 volt drop for each of these reds. Okay, so no matter which way you go, it's going to be 4 volts. Now, when we get to these sort of bicolored nodes, right, the red and black, what happens? Well, the current splits. Okay, splits in two. And then we get recombinations, and I'll come back to this in just a sec. But I want to jump ahead because when I look at the blue end, what I just said about the red is still true. I have three paths that are recombining back to ground. So this has to be 12 mils. And again, because of symmetry, these three currents in the three blue paths have to be the same value. So guess what? These must also be 4 milliamps apiece, meaning each one of these branches has to be 4 volts. Now what happens with the black? Well, the black, that's a split. And again, because of symmetry, each one of these black runs, right? Again, that represents a resistor, right? Each one of those are going to have to be the same value, but it's going to be half of the entering current because it's going to split equally. So I had 4 coming in, so it's going to be 2 down and 2 across. Or if I came in this way, right? 4 in, 2 across, 2 down. If I came down here, it's going to be 2 across, 2 diagonally. And notice at each of these blue and black terminals, you're going to have 2 of the black coming in, right? Over here it's these 2, and over here it's these 2. So it's going to be 2 plus 2 is 4, which is what we already said as far as the blue is concerned. So if I have 2 milliamps in each one of the black ones, 1K, that's going to be 2 volts. So I should get 4 volts across this, 2 volts across this, 4 volts across this. I should get 10 volts back here. Right? So no matter which way you go, right, it's going to be red, black, blue. We already figured that out, right? Red, black, blue, or red, black, blue, red, black, blue, red, black, blue, red, black, blue. So it's always going to be 4 plus 2 plus 4. It's always going to be 10 volts. All right. Well, let's verify. That's what, that's what the hypothesis is. So let's plug it in. Okay. Richard Feynman, the late great physicist, once said that it doesn't matter how smart you are, it doesn't matter how beautiful your theory is, if it's not verified by experiment, it's wrong. The end, right? So let's go and actually see what we get. Oh, look, we got 10 volts. Okay, let's check our current. So this was that first corner node. Let's see what we get here. 4 volts, 4 mils coming in like this. Okay, so proper direction, 4 mils, 4 volts. Down here again, 4 mils, 4 volts. And then these would have been the blue ones. 4 volts, 4 mils, 4 volts, 4 mils, 4 volts, 4 mils. And then, we have the splits, right? So this would have been a black, one of the black paths. That's 2 volts, 2 mils, same thing over here. Okay, so right, this was the 4 coming in, so it's going to split this way and this way. That's also 2 volts and 2 mils. And you can go through, on each one of these things, right? 2 volts, 2 mils, 2 volts, 2 mils, and on we go. All right, beautiful. So what have we learned? Well, we have learned it's Kirchhoff's current law. Notice we did not have to use some technique to find out what the total resistance is. People fall right into that Ohm's law trap. Oh, I need to know the voltage. I know the current, so I have to find out what the resistance is. No, you don't, right? We did not calculate what the effective resistance of this thing is. I mean, we can do it now because we know there's 10 volts, right? We can now say, well, that's 10 volts, 12 milliamps, right? It's 5/6 of a K ohm, and we go from there. But we didn't have to. We didn't have to figure out what the effective resistance of this whole thing is in order to find the voltage, right? So don't fall into that trap. Sometimes just doing something a little different, a little weird like this can help you get out of those sort of habits. Okay? All right, so there's more to be had. So stay tuned for Network Fun number 3. Until then, take care.